We now want to continue our discussion of the integral test by using Riemann sums, the left Riemann sum and the right Riemann sum, with improper integrals to approximate the error in approximating the sum of an infinite series. So let me say that again. We saw in the last video that the divergence test, if the limit of the sequence doesn't go to 0, then the series definitely diverges. The tail values of the sequence have to be practically 0, but there's no way it adds up to a finite number. But that alone is not enough. We saw with the integral test in the P series that in fact, the graph has to get low enough, fast enough, in order for the area under the curve to be finite. And if the area under the curve is going to be finite, then we can use the comparison test to establish that, in fact, the series has to be doing the same thing, also has to be finite. So if the integral and the series both converge, it may not be to the same value, or they both diverge, right? So they do the same thing. But there were 3 conditions. The terms had to eventually be all positive. The function, when you took out the index n and replaced it with the variable x, had to be continuous at some point on, so for the tail of the series, and it had to be decreasing. Again, not necessarily at the beginning, but for the tail, for some value of uppercase n to infinity, all the terms had to be positive, it had to be continuous, and it had to be decreasing. And if that was the case, then if the improper integral converged, then the series would converge. And if the improper integral diverged, then the series would diverge. However, because the convergence does not tell us what it converges to, we still have no idea what the infinite sum is. So we want to now talk about how do we approximate this infinite sum. When we approximate it, there's going to be some error involved because we're approximating. And we're going to use left and right Riemann sums and improper integrals to put boundaries, an upper bound and a lower bound on this error so that we know how far off we are. Now, what we're going to do in this particular case is we're going to say that instead of taking the infinite sum, starting at some n value and going to infinity, the infinite series, if it converges, we're going to approximate the infinite series by only adding up the first uppercase n terms. So what are we doing there? Well, we're saying that since all the terms in the sequence have to eventually go to 0, the tail has to be practically 0, not exactly 0, but practically 0, then the sum of the infinite series, the actual value of the sum, has to be coming from mostly the head of the series. The tail determines convergence or divergence, but it's the head that really determines the value of the infinite sum. So we're going to take the first uppercase n terms, and we're going to use their sum to approximate the infinite sum. Now, what we're doing is we're taking the infinite series from wherever we started to infinity, and we're subtracting the first n terms off, and that would give us, in fact, the remainder or the error involved. And we call this R sub capital N, because again, we're taking the first n terms to be our approximation of the infinite series. So this would be the sum from lowercase n equal to uppercase n plus 1 to infinity. So in other words, we're looking at the tail, and the tail becomes our error. It's the remainder. It's the part we're not including in our approximation. So let's take a look now at what this would look like if we were to write it out. Now, I assume that this particular sequence was starting with n equals 0, but again, it doesn't have to start at 0. It's the same idea. So starting at 0, if the series is convergent, adds up to a finite number, then we know S infinity is a finite number. So it must be that the sum of all the terms of the sequence forever and ever add up to this finite number. But if we take the first uppercase n of them, which is the head of the series coming from the front, we can use that to approximate our infinite series. Let me share my screen with you so that you can see a little bit closer exactly what I'm looking at. So now when you're looking at this, you can see that in fact, it's the head of the series that gives us the most value, because the tail of the series, these terms are getting super close to zero. They're not zero, but they're super close. And so it's adding up to a very, very small amount. So the vast majority of the value of the sum of the infinite series comes from the head of the series. So we're going to use the head as our approximation, and that makes the tail from uppercase n plus 1 to infinity the remainder, or the error. This is the part we didn't include in the approximation. It's the tail of the series. Now, provided that the infinite series meets the conditions of the integral test, eventually all positive terms, eventually continuous, eventually decreasing, then we can use Riemann sums to approximate the infinite series and estimate this error r sub uppercase n. Now, for convenience, we're going to start our series at n equal 1, but that is not required. Now, it could start at any particular n value from 0 up, as long as it was an integer value. The reason I chose n equal 1 is so S1 is a sub 1 and S2 is a sub 1 plus a sub 2. I wanted the subscripts to match, so that made it a little bit easier. So when I'm looking at this, the sum from n equal 1 to uppercase n of a sub n, the remainder of the infinite series starts at n plus 1 and goes to infinity. So this is the part I'm not including in my approximation. But S infinity, because I know it's finite, has to be the sum of the first uppercase n plus this remainder. Those two added together have to give me the true value of the series. And I can write that, of course, in this expression as well, right? So that basically breaks it into the two different parts. Now, we know that the left Riemann sum is going to be an overestimation, and we know that the right Riemann sum is an underestimation, because by the conditions of the integral test, the function has to be decreasing. So the left Riemann sum overestimates and the right Riemann sum underestimates. Now, the right-hand sides on the right Riemann sum, when we start at n equal to uppercase n, are going to represent this sum right here, the sum from n equal n plus 1 to infinity of a sub k. In other words, this is the remainder, right? Again, we're starting with lowercase n equal to uppercase n, but we're doing a right Riemann sum. So we use the right endpoint of the intervals, but that right endpoint is a sub n plus 1, a sub n plus 2, a sub n plus 3, and so on, because I chose for my subscripts to start at 1, so they match, all right? Which basically then gives me that the remainder is this sum from a sub n plus 1 and so on, using the right Riemann sum starting at lowercase n. Now, the left-hand sides of the left Riemann sum, but not starting at n, starting at n plus 1, so starting one further out. The right Riemann sum starts here, but it uses the right endpoint. The left Riemann sum starts at uppercase n plus 1, but it uses the left endpoint. Notice it's giving me the same values, a sub uppercase n plus 1, a sub uppercase n plus 2, and so on. They're the same points, right? So if we're looking at this, we can see this, and I'm going to shrink up my page here so that we can see them on the same page. Do you see that it's using exactly the same point? It's not the same area, right? This is a left Riemann sum starting at uppercase n, or right Riemann sum starting at uppercase n. This is the left Riemann sum starting further to the right at uppercase n plus 1. But they're both using the height at a sub n plus 1, the height at a sub n plus 2, the height at a sub n plus so on. They're using the same locations to generate their values. They're the same place. And these, of course, are going to represent the error because this is basically R sub n. This is the sum from lowercase n equal to uppercase n plus 1 to infinity. So let me blow it back up again so that we can see what it looks like. And again, what we have here is this approximation where the right Riemann sum starting at uppercase n and the left Riemann sum starting at uppercase n plus 1 give me the same values, which is that error. Now, I know that the left Riemann sum must have more area than the corresponding integral. Why does the left Riemann sum have to have more area? Well, let's look at the left Riemann sum again. It has to have more area because it's a decreasing function, so it's an overestimation. So that means that it's got to be greater than or equal to the definite integral. It's an overestimation starting at uppercase n plus 1, right? So again, I'm going to shrink the page so we can see both of these on the same slide. So when we're looking at these, the one on the bottom in green represents the true area under the curve from uppercase n plus 1 to infinity. This is the improper integral from uppercase n plus 1 to infinity of f of x dx. The one above it, however, is the left Riemann sum, which is an overestimation of that area. So there's more area in purple than there is in green. Now let's take a look at the right Riemann sums. Now we know the right Riemann sums on a decreasing function are an underestimation. But this time, remember that the right Riemann sums didn't start at uppercase n plus 1. They started at uppercase n, so they started further to the left. But again, they're using the same points as the left Riemann sum starting at n plus 1. So when we look at this, we can see here that this area in orange is the improper integral from uppercase n to infinity of f of x dx. And this has to have more area than this Riemann sum, and this Riemann sum represents R sub n. The error, if I take the first n terms, a sub 1, a sub 2, a sub 3, a sub 4, all the way up to a sub uppercase n, and I use those to approximate, this is what I'm not including. This is the error that I have. And this has to be greater than that because this is an underestimation. So now let's put all of this together. So when we look at this, we have the area from uppercase n plus 1 in green has to be less than or equal to the left Riemann sum, which represents R sub n, the error involved, the remainder, the terms we didn't include in the approximation. Again, this is R sub n. This is the error, the terms we didn't include in the approximation, which is equal to, of course, the right Riemann sum starting at uppercase n. This one starts at n plus 1, this starts at n, but they're using the same points in order to estimate. So they're equal to each other. So the area under the curve from uppercase n plus 1 must be less than or equal to both the left and right Riemann sums starting at different places, that error, but it has to be less than or equal to the improper integral from uppercase n to infinity, because this has more area than the right Riemann sum, which is an underestimation. In other words, we've trapped our error, our remainder, between two improper integrals. And these are the two improper integrals that you see here at the bottom of the screen. Our error, the remainder, the tail of the series that we didn't include in the approximation, R sub uppercase n, is trapped between two improper integrals, one starting at n plus 1, which is further to the right, and one starting at n, which is further to the left. The one that starts further to the left obviously has more area under it because you're starting from a lower n value. And this one has less area because you're starting further to the right and it's a decreasing function. In other words, we've now got an estimation of how big the error is if we take the first uppercase n terms to approximate our infinite series. So now let's go ahead and take a look at the theorem, which is called the remainder theorem. And the remainder theorem is going to tell you how to put an upper boundary and a lower boundary, an upper bound and a lower bound on the error. So we're going to let some series of a sub n be a convergent infinite series, adds up to a finite number, and it has to meet the conditions of the integral test so that we can use the Riemann sums to approximate. Let S sub n be the nth partial sum of the infinite series. So the infinite series. So S sub n is the nth partial sum. Now remember, S sub n is basically going to be the sum from the beginning up to uppercase n. So that's what this represents. Then S sub n plus the integral from n plus 1 to infinity, this is the lower bound on the error, has to be less than the true infinite sum, which has to be less than S sub n, the approximation, plus the upper bound on the remainder, all right? So we have the lower bound on the remainder and the upper bound on the remainder. So the lower bound on the remainder plus the approximation has to be less than the true value of the infinite series, which has to be less than the approximation plus the upper bound. So the true value has to be between those two. And I can compute all of these pieces. So the remainder then has to satisfy, of course, this inequality that we saw up above. So let's see how we actually apply this to an example. In this example, we have the series from n equal 1 up of 1 over n to the fourth. So we want to find the approximation for the series using the first 5 terms, that's S5, and then we want to estimate the error. How far off are we? What's the upper bound on the error? What's the lower bound on the error? So when we look at these, we're going to start with S5. Oops. So when we look at S5, again, our subscript is starting at 1. So basically, S5 is A1 plus A2 plus A3 plus A4 plus A5. All right, it's the sum of the first 5. All right, so I'm going to write down what the first 5 are. When n equals 1, I have 1 over 1 to the fourth. When n is 2, I have 1 over 2 to the fourth, plus 1 over 3 to the fourth, plus 1 over 4 to the fourth, plus 1 over 5 to the fourth. Now, this is my approximation for the value of the infinite series, which goes to infinity, but I'm approximating it with the sum of the first 5. So I'm approximating this with the sum of the first 5. And this, of course, is S5, right? So I'm approximating it with the first 5. Well, take your calculator out and figure out what you get. And basically, you're going to end up with something that's relatively close to 1.080352, right? So this is an approximation for the value of the infinite series. If I took all infinitely many terms and added them up, I'm saying I would get approximately this number. Okay, so I've estimated the infinite sum. Now I want to estimate the error. How far off could I be? So in order to do that, I want to estimate the error R sub 5. So to estimate the error using the first 5, this has to be between the integrals starting at 6, one more than the subscript, going to infinity, of 1 over x to the fourth dx, and less than the integral starting at the same subscript, 5 to infinity, of 1 over x to the 4th dx. This is what we proved previously. As long as it met the conditions of the integral test, the remainder, the error, is bounded by these two improper integrals. So again, this subscript 5 corresponding to using the first 5 terms, the upper bound starts at the same subscript and goes to infinity. The lower bound of the error starts at 1 greater and goes to infinity. Now go ahead and pause the integral and find the value of both improper integrals, then turn the video back on and we'll compare our answers. Let's see how you did. So again, what we're trying to do is establish an upper bound on the error in approximating the infinite series using the first 5 terms. So I'm looking at r sub 5, the remainder, the terms I didn't add up, the ones from 6 out. So I take the integral from 5 to infinity of 1 over x to the 4th dx as an upper bound, and the integral from 6 to infinity of 1 over x to the 4th dx is a lower bound. Now they're the same integral, just with different limits of integration. So once you establish what one of them is, you have the other one as well, but with different limits of integration. So basically, I worked out the one on the left, which led to 1 over 648, which is a finite value, which I should get because this is a convergent series. Now, 1 over 648 is about 0.0015. It's a little bit off, but it's close to that. And on the right side, my upper bound turned out to be 1 over 375, which is 0.0026 repeating. And so I have an upper bound and a lower bound on the error involved in approximating my infinite series with the sum of the first 5 terms. Now, I got the sum of the first 5 terms to be about 1.080352. If you want, you can get a common denominator there and write it as an improper fraction. It's going to be pretty nasty, but you could do it if you had enough time. And this is now telling me how far off that 1.080352 is. It's at least 0.0015 off, but it's no more than 0.0026 repeating off. So I have an upper bound on what the values could be. It's got to be at least between these two. So it's got to be somewhere in that range. All right. This is the error. This is the boundaries on that error. Now let's see another way to find a particular sum to within a certain degree of accuracy, because this is more likely what we would be doing, which is I have an infinite series and I want to approximate the sum of it, but I want it to be accurate to within a certain amount. In this case, I want it to be accurate to within 10 to the negative third, which would be 1 over 1,000 or 0.001. Now you could choose any value. The choice here is totally arbitrary. So this could be 10 to the negative 8 or something like that. You want it to be small, right? You want your error to be small so that your approximation is fairly close to the true value. So what we're doing is we're putting an upper bound on the error term, not a lower bound, but an upper bound. So we want the error to be smaller than 10 to the negative third. So how do we work this out? Well, what we do is we go ahead and write down the boundaries on r sub uppercase n. So we're looking to find n. We want to find the value of uppercase n that restricts the error to being smaller than 10 to the negative 3. So this is going to say that the error is going to be between uppercase n plus 1 and infinity of 1 over x to the 4th dx, which has to be less than r sub uppercase n, which has to be less than the improper integral from uppercase n to infinity of 1 over x to the 4th dx. So this is what we found previously, as long as the integral meets the conditions of the integral test. And we've established that this one does. It does have a convergent sum. We know that because it's a p series, right? N to a power, and the power is greater than 1, therefore it converges. So we know it converges by p series. We could also use the integral test, and we could establish convergence. So we've got these boundaries on our remainder, and the one we're concerned with is the upper bound. We want this upper bound itself to be less than 10 to the negative 3. So we're sort of discounting the lower bound, and we're just focused on the upper bound. Now we're going to reuse the material that we did above, the work we did above, and we're going to say that this integral from n plus 1 to infinity of dx over x to the 4th, which has to be less than r sub uppercase n, has to be less than, and then what we're going to do is we're going to substitute in, of course, the limit as c goes to infinity of the integral from n to c of dx over x to the 4th. And we're going to use what we had up above in order to find those values. So again, coming to what we did up here, remember that what we ended up with was 1/3 times the limit as c goes to infinity of 1 over x to the 3rd from c to whatever the upper bound or the lower bound originally was. So we have 1/3, and then we have the limit as c goes to infinity of 1 over x to the 3rd between c and uppercase n, right? So that's the value of that upper bound on the error. Now we want this to be less than 10 to the negative 3. So what we're going to do is we're going to go ahead and evaluate this limit right here. We know what this is going to give us. Coming down here, we have 1/3, and then we have the limit as c goes to infinity of 1 over n to the 3rd minus 1 over c to the 3rd. And we want this to be less than 10 to negative 3. And again, we're more or less ignoring the lower end of the inequality. We're only concerned with the maximum error involved, which we want to be less than 10 to the negative 3. Now we know as c goes to infinity, the denominator goes to infinity, so the fraction goes to 0. And this allows us to write, since uppercase n is a constant, this allows us to write 1 over 3 uppercase n cubed has to be less than 10 to the negative 3. Now, writing 10 to the negative 3 gets a little tiresome, plus 10 to the negative 3 isn't really in fraction form, so we want to rewrite this in fraction form. So what we do, of course, is we simply write it as 1 over 10 to the 3rd. Now we have to think about what the value of uppercase n is. Remember that this was based on a series, which started, I believe, at 1, in which case uppercase n is strictly positive. And because it's strictly positive, then I can multiply both sides by 3n cubed, which must be positive. And of course, 10 to the 3rd is positive, so I can multiply both sides by 10 to the 3rd. So when I multiply both sides of the equation by the denominators, 10 to the 3rd times 3n cubed on both sides, then I end up canceling on the left the 3n cubed, and I get 10 to the 3rd is less than 3n cubed. And notice the sense of the inequality does not reverse because these were all strictly positive values. Now I'm trying to find uppercase n. So the next thing I want to do is I want to try to solve for uppercase n. So the first thing I'm going to do, of course, is move the 3. And this gives me 10 to the 3rd over 3 less than uppercase n. Now I know n is strictly positive. It wouldn't matter because it's a cube root. And so when I take the cube root, I get the sign I get. I know it's going to be positive because I know uppercase n is positive. So I'm going to take the cube root of both sides. And when I take the cube root of both sides, I get 10 over the cube root of 3 less than uppercase n. Now grab your calculator and punch in that value, and write down what you have as an approximation for that. So it turns out that 10 divided by the cube root of 3 is about 6.934, and it keeps going. It is, of course, an irrational number because of the radical. And so we want our subscript, which has to be a positive integer value, to be larger than that. Now, to guarantee that the error is going to be less than 10 to the negative 3, I need to choose some value that's larger than this. The smallest such value that I can choose is n equals 7. Now, could I choose n equal 8? Yes, you could. If you choose n equal 8, it will definitely be less than 10 to the negative 3. In fact, it's probably less than that. But what guarantees the smallest possible n value that guarantees it is 7. So if I want the error to be less than 10 to the negative 3, I can approximate the infinite series with the sum of the first 7 terms, and then the error on the remainder will be less than 10 to the negative 3. So this concludes our discussion of the integral test and the divergence test. And in this video, we were focused again on putting boundaries on the remainder when we use the first uppercase n terms to approximate the infinite series. In the next video, we'll be taking a look at what are called the comparison tests, the limit comparison test and the comparison tests. I hope you'll join me to see that video.